All right, Advanced Math 8, we have our last lesson in Unit 4. It's lesson 4.2.4. So this is going to be interpreting correlation in context. So we'll see over here that we have 4-92, and previously we saw in other problems that we've done in other lessons that there was a association between somebody's height and their forearm length. Remember we talked about that was like a cubit length that ancient people used for measurement, and we saw that it wasn't a very good correlation, but anyways, we did it anyways. Karen is coming along, and she's curious whether height is associated with shoe size. So she didn't want to, like, everybody take off their shoes and then have to measure smelly feet. So she decided, hey, you know what? I'm just going to measure the shoe size because that's going to be a little bit easier. So she's going to get all this data here. Woo, that's a lot of stuff to type in. And she's going to look at the least squares regression line and then look at the R value. And now we have something new, the R squared value. So we're going to look at those two and find out what the R squared value means for us. Now, because I'm a heck of a guy, I've got my best friend, Desmos, and I've already done everything for you as far as plugging in all your data set. So here's that huge data set right there, and here's all those points. So remember, she's comparing the shoe size, so that's our X, and she wants to see if shoe size and height over here in, what's that, centimeters? Yep, height in centimeters, see if those two are associated to each other. And looking at that data, I'd have to say, yeah, there looks like there's some kind of association. It looks like it's going to be linear. It looks like maybe moderate to a strong association going on here. Yeah, it's positive. It's going from left to right, up. It looks like as shoe size increases, yes, indeed, the height increases. Looks like they're associated with each other. So let's go ahead and go over here and type in our least squares regression line. Thank you, best friend Desmos. You have just done my least squares regression line for me. So it tells us that our least squares regression line should have a slope of 3.96788. Oh, Desmos, you're so exact. Let's go ahead and round that. Let's say our slope is going to be 3.97. And then our y-intercept, 131.232. Let's just make it 131, just for funsies. All right, so we've got an R value right here of 0.8617. And now we've got this new value called the R squared value, and it's 0.7424. So let's go ahead and write those down and then talk about what it all means. Okay, so I'm going to move this, and let's write down our data values. So starting with the least squares regression line, that's going to be y hat. That's our predicted values. Our slope was, we said it's going to be 3.97, because I'm going to round it a little bit. And then my y-intercept is 131. Looks good enough. All right, there's my least squares regression line. It says that the slope is 3.97, and it says that the y-intercept is 131. Now remember what these mean. The slope means that the height is going to increase by 3.97 centimeters for every increase of one shoe size. So that's what it means. The y-intercept means when we have a shoe size of 0, that our height should be 131 centimeters. So that's what our least squares regression line is telling us. Now our R value for this one was 0.8617, and our R squared value is 0.7424. 7424. All right, now we're going to describe the meaning of the R value and the R squared value. Now you can look into your book on the methods and meaning section, and it goes into a little bit more in depth of what these mean. So I would highly suggest that you go in there and look it up and kind of read through that section. But since we don't have a lot of time, let's just decide what they mean. So in context, we can see that the R value means that there is a moderate to strong linear relationship, linear positive relationship between shoe size and height. So remember, if it's close to 1 or close to -1, that means the strength is pretty strong. I mean, if it's 1, that means it's perfectly in a line. These aren't perfectly in a line, that's why it's not 1. So the R, in this case, means that the strength of the association between shoe size and height is positive because it's a positive R number. That means it's increasing from left to right. And strong to moderate, strong to moderate, for a linear association, for a linear model. So we were just checking with Desmos to see, hey, we made a line. Desmos, what do you think? Should we have used a line? Is it pretty strong for making a line? And Desmos came back and said, well, you got an R value of 0.8617. So what does that mean? It means that we've got a pretty strong association between shoe size and height. It's positive association because it's a positive R value, and it's pretty strong, I'd say moderate to strong, for the linear model. Now the R squared value means something completely different. Now by itself, the R value really doesn't mean anything as a number. It's just used for comparing two different scatter plots. So an R value on one scatter plot that's higher than an R value on another scatter plot just means that that data is closer to the least squares regression line. R squared actually has a meaning by itself. The R squared value, remember we talked about causation. In causation, we said sometimes there's some lurking variables in there, and they're causing some stuff to happen. Well, R squared tells us how much, what percentage of the association can be attributed to just shoe size and the height. So the R squared being 0.7424, that means that 74.2% of the variability of the height is caused by shoe size. That's kind of a nice number to have. So this is telling us that, okay, there are other variables involved. There's some hidden variables. There's some things affecting our graph here other than these two variables, but we can say that 74% or 74.2% of the height is caused by shoe size. Now, there's other factors out there. Maybe people are wearing shoes that don't really fit them. Okay, so you can wear a shoe that's not fitting you. Maybe you have grown out of your shoes, but you're still wearing them, and your toes are all scrunched up at the end there. So maybe that's a factor that is affecting it. Maybe just foot size does not affect height. Maybe there's some tall people out there with really small feet. So maybe those other factors are in there. But what the R squared value is telling us is that 74% of the difference in our model is attributed to the height caused by the shoe size. So if only a portion of the variability in the height can be explained by shoe size, what other factors might go into determining someone's height? So it might be genetics. Maybe their family members just have small feet and really tall. So maybe genetics comes into it. Maybe people wear the wrong shoe size. So wearing shoes that don't fit. So this says that 74% of the variability is due to shoe size, but that means that 26% of the variability is due to other factors. Maybe it's genetics, maybe people wearing different shoe size. Fill in your reason there. It could be a whole bunch of different things that are happening. All right, so R squared tells us what portion of the variability of the height, so what portion of the Y value is explained just by the X value. All right, so we've got a new one here. Let's suppose that Elise collected the following data from 5 random students. Now, this is kind of something you don't want to see in statistics. You don't want to see small groups of data. You want to see larger groups of data because that'll give you a lot more variability. So this person's probably not making a good decision here. She only takes 5 people in her class. So she's got 5 people, puts down their shoe size, and then their height. And we want to see what happens to those. Okay, so I made another Desmos because I'm so good. And here's our new data that Elise did. And looking at that, oh my goodness, it looks like it's a straight line. It really does. Well, let's make a least squares regression line for it and see if it is indeed a straight line. There you go. Stupid thing gets in my way. I can't figure out how to make it move. You're killing me. Okay. Now it's not making me move. Okay, there's my least squares regression line for this one. Whew, it's going right through the points. There's no residuals. Okay, so what's the correlation coefficient for this one? The R value is 1. Remember what that meant? And why is this unusual? Okay, so our R value is 1. That usually doesn't happen because that means that there's a perfect correlation between the shoe size and the height. So it's 1. Why is this unusual? There is no variability. In the data set. It is a perfect positive association. All right, so this is supposed to be data where stuff doesn't make a perfect line. So this is odd. This shouldn't really happen a lot. There's no variability. All the data is in a perfect line. There's no residuals. That's what we're talking about with variability. It's all in a straight line, and the R value is 1. In context, what does the correlation coefficient tell Elise about the association? And we just said it, that it's a perfect positive association. So what this tells us is that there is a perfect positive association. Meaning there are no residuals. All of our actual heights were also our predicted heights. Okay, what can she say about the variability in her height in our class? Now the R squared value was 1. That means 100% of the variability in her height is due to shoe size. That means there's no other factors out there. 100%. Whatever your shoe size is going to determine your height exactly. So this means that 100% of the variability of heights is determined by shoe size. Which is ridiculous. There's no way that your shoe size would tell you how tall you are. That's crazy, because we all know of somebody else who has the same size shoe that we do, but is a different height than us. So she probably just didn't get enough data to put in there, because there's no way that your shoe size, that's hard to say fast, your shoe size will explain how tall you are. All right, 4-94. Holly created a scatter plot for her class. Here it is. Now she's comparing the score on the Chapter 5 test with people's heights. And this is her scatter plot. Oof, that doesn't look real good. So what do we notice about the pattern of this data? I don't see any pattern. The pattern seems to be random. I mean, if I had to guess at a pattern, I'd say maybe that it's decreasing a little bit. Maybe. I don't know. It's really hard because that data is all over the place. And what do you think? What do you think the correlation coefficient is? Well, I think the correlation coefficient should be pretty darn close to 0. So the R value should be close to 0. Because it doesn't look like there's a positive or negative association in this data. It just looks like it's random. What can you say about the variability of the girls' heights in Holly's class? Well, we can probably say since the R value is close to 0, the R squared value will probably also be 0. Probably. I always find probably hard to spell. I don't know why. Will probably be close to 0. Which means that almost 0% of people's heights is being determined by the Chapter 5 test score. So almost none of the heights are being determined by test scores. All right, last problem. We are back to the Julia problem. Last time, had to do it. We've done it like in 5 different lessons. So here we go. We got Julia problem again. She's got all her toppings for pizza and all the prices. We've done this all before. The least squares regression line for this one was y hat is equal to, we'll just call it 1.36 plus 7.74. Yeah, 107. So that's close enough. All right, so that's the least squares regression line. Now let's look at the correlation coefficient and the R values. So I've already done it for you. This is a problem we've looked at several different times in several different ways. And going over here, I've got, oh, that stupid thing again. There we go. There's our least squares regression line. It tells us the slope over here is 1.35 or 1.36. We're going to round that. And 7.74 sounds good. We're rounding there too. All right, it does give us an R value. So go ahead and write that down. The R value is 0.8616. So the R value is 0.8616. And the R squared value is 0.7424. All right, so let's go back to our notes now that we've calculated all that. Okay, so we've got our R value of 0.8616. Our R square value is going to be 0.7424. Now remember what the R value means. The R value deals with the strength of the data. How strong of a association are we seeing with our data? So in this case, we are probably seeing a moderate to strong association. Since this number is positive, we're probably also seeing the slope is going to be a positive slope on there. So it's going up from left to right. So as the toppings are increasing, we should expect the price to also increase. Okay, so we've got all that in there. Okay, so what we can say now is that we describe the context using the slope, the y-intercept, the r, and the r squared value. All right, so we can say that the slope in context means that for every topping, or we can say the price, let's say the price increases by $1.36 for every topping added. Let's look at the y-intercept. The y-intercept in this situation says that when we have 0 toppings, we should have a price of our pizza of $7.74. I guess that's like cheese pizza. Okay, so what is our R value telling us? The R value, being at 0.8616, says that there is a strong to moderate positive, it's a positive number, linear, because we did a linear model here, association, between toppings, number of toppings, and price of pizza. And finally, we've got our R squared value. Our R squared value is saying that 74% of the price variability, so 74.2%, is due to the number of toppings on the pizza. So that means that there's other factors out there that are changing people's prices. Maybe somebody has a higher rent at their establishment, and that's why they need to charge more for their pizzas than other people are doing. Maybe somebody gets their ingredients cheaper or uses cheaper ingredients, and that's why they don't have to charge as much for their toppings. So that would be where the other 26% of the variability is coming from. So there's some other lurking variables out there that could change the cost of the pizza based on the toppings. So there's other things out there, but most of the variability is due to the toppings on the pizza. All right, I got to go. That bell means that I have to start class. Okay, see you guys later. Math hard. Be good.